All right, good afternoon, my EM aficionados. It's the first day of October 2025. I am 8 weeks after my surgery, no longer in the sling, and slowly but surely recovering. Today, I wanted to show you another final thinning method for doing lamella prep. And this is an interesting one because this is one that I've actually known about for a while and actually just recently started attempting. So let me show you what I've got here. So I've got a silicon-based lamella, and you can see I've actually welded this to the side of the post rather than in the notch. Okay, so the videos I've shown up to this point, I did welding in the notch. So the reason I like to do that is you can keep the lamella from bending because you can constrain it on both sides. Okay, so that's the idea. But what I've seen some people do is they actually mill what's called a stability bar into the lamella, and it prevents it from bending, and then you can mount it on the side like this without mounting it in the notch. So this has some advantages if you mount like this. So for one, it's faster because you don't have to do as much prep to the grid. So there's that. The other thing is that if you mount it like this, because you don't have the grid underneath it, you can tend to be a little bit less prone for things like re-deposition. So there are some potential advantages to this. The main disadvantage, though, if you just thin normally, is bending. Okay, this lamella is going to bend when it gets thin. So you have to have some way to actively restrict it from doing that. So the way to do that is with what's called a stability bar. So if you look at this, you can see this is a fairly thick initial lamella here, right? And this is necessary for this approach to work. You can see this is about 4 microns-ish thick. I'm already at eccentric height, but I'm going to go ahead and pitch back. Yes, so I'm edge on right now at 1/2 degree. So then 51.2 or 0.5 is going to be my parallel, or I should say, yes, normal incidence, normal to the, well, parallel to the sides of the lamella, normal to the top of the lamella for the fib beam. Okay. Okay, so now what we're gonna do, and let me switch to the SEM. So I've got, or the fib, sorry. So I got the 1 nanoamp beam here. I'm of course on the Helios Nano Lab, and I'm gonna go ahead and beam shift up here, mag, go ahead and give it quick focus and take a snapshot, okay? So what I found, what we're gonna do basically is this backside here, we're going to use a rectangle and we're going to mill down part of it, okay? So we're not gonna mill it completely off. We're just gonna mill down part of it. So we're seeing, this is the side, we have a 180 scan rotation. So when we mill the top in the fib, we're seeing the bottom side, or the viewable side, if you will, in the SEM, okay? So we're going to use the rectangle here, and we want to put this, so you can see I actually left some extra silicon space here, and you don't want to push this all the way across, like all the way across the lamella. You want to leave some material on either side. So that's about probably, how much is that? Yeah, it's about 2 microns on either side. I mean, we could probably, we could do 10.5, maybe just a little bit here, but that should be okay. All right, and then for the depth, I'm gonna put 2, and we're actually just gonna monitor this here as it's going, okay? But basically, we're gonna cut this away till we see like a ridge, and we want to make sure that the ridge doesn't go all the way through, right? So hopefully this will make sense when we're doing it. I'm just going to take snapshots here, okay? So every just few seconds here, I'm going to take a snapshot just to make sure. So I'm not over tilted at all right now. I'm at 51.5 degrees, which in this case is normal incidence for the fib. You don't want to be over tilted or under tilted for this. You want to be parallel, or just edge on, if you will. Okay. All right, so we're getting close. Okay, now one thing I can do, I can stop this here. Let me take a snapshot with this. Okay, so let me move this in just a little here, just to kind of clean this up. So that's actually underneath, I think, but we're fine. Okay, let me go back here. I'm sorry, I needed to take a snapshot here. The point is, right, we don't want to cut all the way through, okay? We don't want to cut all the way through. There's a little bit there. So here, we can actually, let me mill this. I think we're probably okay. We have all of this on the bottom here, but let me go ahead and, because this is a thin film, like right up in here, this is the area of interest, but here we can mill this away just to see. Okay. Yeah, I think once this is done, here, I'm gonna clear this off here, and then yep, that should be enough for what we need to do. So I should have, would have been better to probably make this a little shallow. Well, we can still make it a little shallower, actually. I find that the thicker you can make that stability bar, though, the better. So this is actually not too bad right here. Let me go ahead and run this again. Especially if you're looking at a thin film, right? You don't need much of a window there. So this is plenty for what we're gonna need here. So, right. Okay, perfect. Okay, so this is our stability bar here. Let me take a fib image. There you go. Okay. So in the fib, right, this is a solid chunk here, and now it's milled down, so we're not obfuscating the side of the lamella, especially up here, but now this is now continuous solid material, like right here, okay? So what's gonna happen as we thin this, right, is that this is going to brace the sides and prevent the bending, okay? So let's go ahead and we can go through thinning this, and hopefully it works. So now we're gonna go ahead and I'm gonna over tilt 2 degrees, 53.5, and I'm gonna switch up to 3 nanoamps, and we're gonna go to the cleaning cross section. And now if we mill through the lamella, it's no problem now, okay? We've got the stability bar, that's gonna be intact, so there's nothing to worry about. Oops. Top to bottom. Okay, let's see here. We can do 4 for this. No, we can do 5, that's fine. And we'll go ahead and monitor this with iSpy. So now iSpy will automatically take snapshots, in this case after each interval in the cleaning cross section. So I actually tested this on 2 samples. The first one came out really good, the second one didn't, and the second one, it actually bended a bit, and I think it was because I didn't have as good of a stability bar here. So hopefully I ironed out the kink there, and this will work better now. The actual lift out I did with PFib. Okay, I'm gonna stop it there. All right, so now I'm going to relative rotate. Now, because we had to pitch minus 0.5 degrees, we have to add a degree when we relative rotate. So I'm gonna go to 54.5, and now that's gonna be plus 2 degrees for the opposite direction. And then I'm gonna relative rotate 180. We're going to do the same thing from the other side. And now with the other side, you know, it doesn't matter. We can mill through the whole sidewall because we have the stability bar. Again, I've seen these in some brochures, some presentations. I've never actually tried this though until now. But I was very amazed at how well it worked the initial attempt I made. There we go. Let's see if we can chop that down a little. Okay. I'm going to stop this once I see the SEM PT layer here, which I don't quite yet. Mag in here. And I'm just going to alternate these cuts. I'm at 30 kV right now. I'm going to alternate, at 2 degrees over tilt and do the relative rotate each way. In case we can start to see this MPT. We want to make sure it's nice and thick here, and then we'll go to the other side. Okay, that's good. Okay, looking good. And so now we'll go back to 53.5 and then relative 180. Again, make sure you have compucentric rotation checked and enable safe stage moves checked. And I'm going to drop my current down to a nanoamp. Go ahead and just tune up my SEM image here really quick. Okay, looks decent. Okay, got a nice thick stability bar there. And focus on the top. stagger the cut here. And we'll go ahead. At some point we will mill through the bottom, and again, it won't matter because we have the stability bar. Okay. I'm trying to take some notes here. This is a video I've been meaning to do, is the video about note taking when you're doing lamellas. I actually have like a template when I do this, so I can keep track of like all the steps, you know, and then take notes and say, hey, the lamella turned out good, right? So you know, remember what you do. There's just so many steps when you're making lamellas, right? It's hard to remember everything. I'm going to stop this probably prematurely here so I can do the other side because the SEM is a little thicker on this side. Okay, I'm going to stop it now. Okay, so now we're starting to almost cut through the bottom. Actually, looks like we are. All right, so we'll do 54.5 and then relative 180. I'm going to cut my current down again by 0.5. So this is in principle kind of like the best of both worlds, if you will. You know, shout out to an old Van Halen tune there. Or, you know, the Hannah Montana song, if you're into that thing. Let's see here. All right, there we go. So far, though, this is looking really good. This will probably be the last step at 30, and then we'll drop it to 8, and then go from there. So you need a little bit more real estate if you're going to do this method, certainly. Getting a weld, you know, again, like I could do a separate video for like how to do a, you know, I call this flag mounting because it looks like a flag waving in the wind. But I could do a separate video talking about how to mount the lamella this way, which would probably be good to do. Again, I lifted these out in the P-fib, right? And then I brought them over here. Keep my finger on the stop button. Is looking good though. So we want to get it to the point here where maybe we're just barely starting to thin the PT. Okay, I'll let it go one more line here and then I'm going to stop it. Okay, there we go. Good. Beautiful. Okay, I'm going to keep the 2 degrees over tilt for the 8 kilovolt step. Again, you know, the choice of over tilting, I mean, there's so many different approaches to that. And then I'm going to go down to 8. I can use I'll use the 0.12 here for this initial step. I might switch down to the 75 picoamps for the next one. Apologies, I'm just noting down what I'm doing here, and then I'm going to cut the depth down here as well. I'm also going to change my overlap. I'm going to boost this up to 90. Change my depth to 3. Oh, I thought that was 4 before. Okay. Was that at 4? No, I guess that was. Okay. I had put 5 in there, so it wouldn't really matter a whole lot at this point. Okay, no worries. All right, so let's go ahead here. Beam shift. Okay, so now you have direct adjustments on. So this looks good. It's not shifting with the wobble here. Go ahead and stigmate. So actually the surface of the molybdenum grid here works great for this. And you don't have to be magged in super high for this. Okay, that looks good. All right. Okay, make sure we're focused on the top of the lamella, which we are. This is better than how the last one, again, it ended up bending, I think, before I got to this point. Again, I think it's because the stability bar wasn't as intact as this one is. So I think that's good. We're not gonna go all the way over. We're just gonna leave it just shy of that, and we're good to go. All right, so I'm gonna turn off spy mode and just go live here because we've got a more favorable SEM to fib current ratio. So this is already looking very promising. Another thing I'd like to mention, so my facility, we're going to be doing a workshop on EBSD, and I'll be sure to put out a link on my community post. It is open to anybody who wants to register, not just the people at my facility or my university. So those of you who are interested, go right ahead. I will be participating in it. I will actually be giving the opening remarks for the workshop, so, which I suppose is makes me a person of some kind of significance. I don't know, maybe not. Okay, so we're starting to see the PT drop, which is good. This has a very thin layer of a metal on it, which was laser annealed. So that's what this customer is looking at. All right, I'm gonna stop it now. Okay, and we're gonna do the relative, or go the other direction. So add 1 degree, and then relative rotate 180. Again, we have to change the actual tilt by a degree because we had to pitch minus ½ a degree to get the grid edge onto the SEM. So therefore, we'd have to add a degree when we relative rotate 180 to get the same geometry. Okay. So that would be 0.5, right? And then you'd have to add 52 to that. So again, it would be a change of 1 degree, right? Because 0.5 minus negative 0.5 would be 1. I remember I did a video about this. All right, let's drop the current down, give us a little bit more control. Go ahead and make a note here in my notepad file here. So this is just a notepad file I'm using for this. I'm sorry, I keep bumping the camera here. All right, let's turn on the modulator. Worse. It's like going to the optometrist. Better 1, better 2. Worse. Okay, and then we can Okay, looking good. Cut this down by another micron. And there's our lamella right there. And there we go. I'm gonna run this till ideally we just have a little, like there's just a little bit of fib PT left, so you can hopefully see that, right? This is the, let me switch to full frame. This is where the SEM PT, boost the contrast here. You can kind of see it's about where my mouse is. So far though, it's looking good. It looks like the first one I did, which turned out really well. The second one, not quite so much. Should still be usable, just aesthetically doesn't look as nice. But we'll see. Hand over the stop button here. Okay, probably let this run the whole way here. We're just about there. All right, let me stop it there. Okay, we got just a little bit of fib platinum left. Take a SEM image. Okay. All right. So I'm actually going to go to 2.5 degrees. We're going to, add just half a degree of over tilt. So that's going to actually be 54 from the other direction. And then row to rotate. And then we're going to drop the current or the voltage to 5. We can keep 48 picoamps. I'm going to change the overlap to 95. And so we're basically going to endpoint the lamella at 5 and then do just a little bit of, dusting off at 2. So with the 2 kilovolt beam, at least on this system, you really, that looks pretty good there. You really have to be careful about not overusing it, because your sample will be very prone to what's it called? Curtaining at lower voltages, okay? So yeah, see the surface of the grid here, this works great for this. Now of course, right, so we can stigmate on the lamella. It looks like there's probably a little bit there still. If you find your stigmators are not working very go to Tools, Preferences, Sensitivity, and then you can change. Now you have to have the fib activated here because that will only adjust that for the fib. But you can see now, right? It's more. You can increase the sensitivity, right? If you feel like you're turning the knobs and they're not doing anything. Okay. All right, that looks good right there. All right, this is going really well. Okay, so have that. I'm gonna back this down a little. Let me bump this up slightly, and we'll change the Z to 2. Okay, have a little movement there. So let's see if that. Okay, that looks reasonable. Okay. All right, make a note here while this is going on. Oops, sorry, bumped the camera there. See, I've become kind of really meticulous with this, with the note keeping. You know, what material file, what's the pattern overlap, because like with this, right, the default overlap on the gallium tool is 50% for silicon, but I will manually change that to, you know, 90 and 95 for doing 8 and then 5/2 kb. It's looking good. So we can't really see it now. When the sample gets thin, it'll be easier to see. There is a thin film of nickel on here, which has been laser annealed. What some people like to do, I've seen people do this where they will start with high voltage, and then as they see contrast change, they will drop the voltage down as the beam becomes transmissive. And you can do that, you know, it's just kind of an extra hassle. We do know that silicon, it becomes transmissive to electrons, 2 kV electrons around 20 nanometers, I believe. You can see down here, this is starting to thin away, which is not a problem because we don't care about that. What we care about is up here. Let me go ahead, I'm going to stop this soon, and we'll go ahead and do the other side. Okay. All right. So now, that's 2.5 degrees. So we have to add a degree for the opposite direction. So we'll go 55. And then relative 180. This microscope, unfortunately, it doesn't have like an auto feature for just like 180 rotation, I believe, compucentric rotation. The newer systems do. It's like a little icon in the toolbar. It's got 2 arrows chasing each other. Okay. A shortcut here for the shift, you hold down the shift key and then left click and drag. You can activate the shift command that way. Okay. And let me see, let's try and focus maybe a little bit better. this down a little. Okay, and let's go ahead and run that. Is that centered? Looks reasonably centered. All right. So now we're trying to endpoint this. So basically, we want just a little bit of the platinum on the surface, okay? Just a little bit. Probably could have positioned that a little better, but that's okay. And we should start to see, as it gets thinner, we should start to see that nickel film come into better contrast. Okay, so we're eating a hole in the bottom. That's not a problem. We don't care about that. We care about up here. You can start to see it coming in here. Okay, we're getting warmer. If we need to repeat this pattern, we can. That's still a lot of PT there. So basically, we kind of want it comparable to the thickness of that film, if you will. Okay, so we still got a little bit left here. So I guess the best thing to do, we still need to thin this more before going to 2. So I guess you can go from the other side. Let's go back to the other side just to be consistent. Sorry. But this is great. It's not bending, it's showing the stability I wanted it to show, so again, it's working out really well. Okay. Yeah, from this angle we can actually see the okay. Cut this down a little bit. So now you're seeing that film become more evident. starting to thin the center PT. So we're going to stop this when there's just a little bit of that PT on the surface. As I said in a previous video, this is kind of like a game of chicken. Warmer. Okay, there we go. Okay. All right. Okay. Yeah, so that is very thin. There's probably just like maybe 100 nanometers of PT left on there, and not bending, right? So looking good. Okay, so from here, okay. So then, hold on, let me do the math here real quick. That's 2.5 degrees, so we'd have to add 55 for that. So then we're gonna add I want to go +4. So we're gonna do 56.5, yes. Because in the other direction, normal incidence is 52.5. Okay, there we go. And we'll relative rotate 180. And then while that's going on, we will change our voltage to 2 and our current to 8.5. And now we're going to switch to the rectangle. Change our overlap to 95%. And now with this, I'm going to use, really small amount here, just to tickle the surface, right? So again, with the low kilovolt, with the 2 kilovolt beam, the curtaining will get really bad, and it's time dependent if you hit it at 2 kilovolts for too long. Okay, so you want to avoid that as much as you can. What we need to do now, though, okay, so now the question is, so it's going to be a little tougher to see. Looks like there's some astigmatism there. Let's see where we're at here. Okay, so it should be this side up here. So now my only concern is, why can't we see it? See, that's the bottom, but we can't really see the top. Okay, it's right about here. Okay, It'll actually be easier the other direction. But yeah, that's where it is, right? You have to kind of follow it along here. So again, we're over tilted by 4 degrees. And I'm just gonna set this for, now you see what I did? I didn't just take a snapshot here, okay? What you can do, right, because the snapshot is pretty noisy, especially when the current's this low. So what I'll do is unpause it, bump up the dwell time, then hit pause, and then, you know, you're gonna see something a bit more meaningful. All right, so it should be right about there. Again, your beam's not very localized at 2 kilovolts anyway, but that looks good, and we'll go ahead. So it's only gonna run for about 20 seconds, okay? Go ahead, hit play. So again, we're really not trying to massively change the sample at this step. You can see the film there. We're just trying to reduce the damage layer, right? You know, a 5-6 nanometer damage layer with a 2-3 nanometer thick damage layer. Okay, and now we're gonna do the same thing from the other side. So we're gonna subtract a degree. It's gonna be 55.5. And then relative rotate 180. Okay, let me take some notes here. 8.9 picoamp. This was definitely one of the mistakes that I made very early, was like going too crazy with the 2 kilovolt milling. At least with this Sidewinder column. Now, my understanding is some of the newer columns, you know, it's a little bit more forgiving for that, but definitely with these older ones, although they still make these, believe it or not. We just got a new Suffice, and they put a Sidewinder on that column. Let me tune up my SEM image here really quick. Okay, looks like we got some astigmatism. Okay, that looks good. Ah, damn it, I accidentally touched the stigmator knob. Okay, there we go. All right, F7 is a shortcut for the reduced area, by the way, or reduced raster, okay? All right. Now it should be, yeah, see in this orientation, it's a lot easier to see because it's, I think it's just facing the ETD a little bit more. But you can really see that where the thin spot is now. Actually, we can try and okay. I'm just stigmating here. All right. As far as 2 kV 8.9 picoamp current settings go, though, that's pretty good. All right, can even maybe bump that down a little bit. So again, this is only running for 0.03 for the Z, so about 14 seconds. All right, there we go. Right, so you can see it is eating away at the bottom. So it is affecting a change in the lamella, which you want. Again, you just don't want it to be like a massive one. And we're done. Nice. Okay, so let me mag out here just to show you the whole thing, right? So there you go. So right now, the stability bar here is preventing, right, any issue, okay? What's it called? Right, if you can imagine, if this wasn't here, there would be nothing to brace this side or keep it from folding in on itself, okay? So that's the whole idea, right? Is by having this in here, you prevent that from occurring, okay? And again, right, we probably could have made this a little thinner, right? This is overkill, but you know, better safe than sorry, right? And the previous versions, actually, I think did I store the stage position? Well, let me go ahead. I'll move over to the other one that I did just before this one, so I can show you how that one turned out when the stability bar was not quite as good. Let's see here. Is that here? It is. Okay, so you can see this one. Right, here's the stability bar. So I thought this was okay, but I think this actually isn't quite that well connected here, but this ended up bending in the middle, and so this should still be usable, but just not as good. So just, I mean, that's just the thing with this, like you wanna make sure that this is nice and rigid, and it appears to be better in the first case. So anyways, that's just an example of the difference there. Yeah, so you can see this is more solid here. This is firmly connected, so provided us with a better result. Okay, all right, so that's the video on final thinning via the side mount or flag mount method using a stability bar. Hope you found that useful, and I'll talk to you all soon.